Hello everyone, welcome to Electronically Connected. First, let's see what topics we're going to cover this time. So we're going to cover what is a diode and its functionality, the construction of the diode as in what materials we're going to use, the working of a diode when it's not connected to any external voltage, that is under no biasing, and then the forward biasing of the diode. So what is a diode? Diode is the most simplest semiconductor device. As the word suggests, let's break it. Di as in two and ode is for electrode. So a diode is a device which has two electrodes, the anode and the cathode electrode. The anode is the positive electrode and the cathode is a negative electrode. Let's understand better with the help of the symbol. This is how a diode symbol looks like. It's an arrow pointing in one particular direction. This is so because it represents the flow of current. A diode is unidirectional in nature. So it allows the flow of current in one direction, where the resistance is low. However, it blocks the flow of current in the opposite direction, and the resistance is high. We can understand the relation between the current flow and the resistance with the help of the Ohm's law, where V is equal to IR and I is inversely proportional to R. Moving forward, let's understand the construction of a diode. A diode is made up of two materials, the P-type semiconductor and an N-type semiconductor. We have learned about what a P-type semiconductor layer is and an N-type semiconductor layer is. So just a recap, a P-type semiconductor layer is made up of trivalent impurities, so it has holes present in them. And the N-type semiconductor is made up of pentavalent impurities, so it has an extra electrons. So let's draw the holes in the P-type semiconductor as the positive charges. We have a bunch of holes because it's doped heavily, and the N-type semiconductor representing the extra electrons in it. Let's connect it to its electrodes. The P-type semiconductor layer is connected to anode, which is a positive electrode due to the holes, and the cathode represents the negative terminal due to the electrons. Let's match this to the symbol that we drew earlier. So a diode symbol is actually made up of P layer and the N layer. So our P is actually the triangle in the diode and the N layer is actually the vertical line. When the P-type semiconductor is bumped with an N-type semiconductor, it forms a junction. This junction, along with the whole construction, is also called as a PN junction, which is literally a junction formed between the P-type semiconductor layer and the N-type semiconductor. Now, as we join these two layers together, there has to be some effect on it. I'm going to redraw it just to explain you better. We have the P-type semiconductor layer pumped with the N-type semiconductor layer. The P-type semiconductor layer has a bunch of holes present in them. Let me draw the holes with a red color. And the N-type semiconductor layer is going to have some negative charges, free electrons as its charge carriers. So here we have them. Now the negative charges and the positive charges, they are obviously attracted to each other, and there's a very large density gradient that exists between these two. As a result, what happens is these negative charge carriers, they migrate over to the P-type. They migrate and they recombine with these holes. As they recombine, they leave behind positive ions, a bunch of them. Also, similarly, my holes, they migrate towards the N-type semiconductor layer and they recombine. As they recombine, it leaves behind negative ions. Now, these negative ions are called acceptors, acceptor ions, and my positive ions are called donor ions because they can still donate any ion and the acceptor ion can accept any ions. this recombination, this first is the migration of my charge carriers from p-type to n-type, or let's say from n-type to p-type, keeps on happening, and there is a recombination of my electrons with my holes and my holes with my electrons. As the migration and the recombination keeps on occurring, there is a huge charge gradient that is formed between it. The net charge becomes different. The electrons, the ions, keeps on increasing on the p-type, and the acceptor, the positive donor ions, keeps on increasing. As a result, we can see that very less number of holes are present in the p-type, and similarly very less amount of electrons are left in the n-type. An electric field gets developed between the n-type and the p-type. It flows right from here. As the electric field keeps on increasing near the junction, it happens near the junction, the electrons from the n-type, it moves towards the peripheral. And similarly, the holes from the p-type semiconductor, it moves towards the peripheral. Let's redraw this to understand better. We have the p-type semiconductor and my n-type semiconductor. Now, the electric field has gotten stronger between the n-type and the p-type. As a result, my positive charge carriers, they line up near the peripheral, they stick to them, and my negative charge carriers, they stick to this peripheral. On the other ions that we have, the donor ions, they are lying about here, spread about, and my negative ions are lying in the p-type semiconductor layer. We can see that there is a different layer that gets formed here where we have the peripherals with the holes and the peripherals on the n side with the electrons. So we have a different layer that gets formed. This layer is depleted of any free charge carriers. So in our n-type semiconductor, we know the electrons are my p-type charge carriers, and in the p-type, the holes are. In this depletion region, we do not have any free charge carriers. Hence, this region is known as the depletion region. Also, there is a potential difference between these two layers, so it's called as a potential barrier. With a potential difference caused between the n-type and the p-type semiconductor layer. This is the basic functioning of the diode when it is not connected to an external source. So let's recap. The positive charge carriers get collected near the peripheral of the p-type semiconductor, and the negative charge carriers get collected near the peripheral, and a depletion region is formed near the junction. So now let's move forward and understand what will happen if we connect an external power source to my diode. So I'm going to first draw it symbolically. We have a diode. This is the p-type and the n side of it. Now, this is what a forward bias connection looks like in the diode. The p-type is connected to the positive terminal of the voltage source, and the n-type is connected to the negative side of the voltage source. Let me redraw this according to the electrons. So we have the p-type semiconductor and my n-type semiconductor. We remember that my holes are collected near the junction, and my electrons are again also collected near the junction. We have my acceptor ions spread out everywhere, and my donor ions present in my n-type there. Let's connect it externally to the voltage source. So the anode is connected to the positive side of the voltage source, and the cathode is connected to the negative side of the voltage source. So as we can see, these holes, the positive charges, repel the positive charge in the positive terminal and the negative charge carriers get repelled by the negative terminal. As a repulsion happens, the positive charge carriers, they start spreading out, and the negative charge carriers, they also start spreading out. Let me draw the depletion region that we had. As a result, my depletion region keeps on decreasing. It decreases. So we can see that because the depletion region is the region which does not have any free charge carriers. So as the positive and the electrons keep spreading out, the depletion region keeps on decreasing. So now, till when does the depletion region keep on decreasing? As we increase the voltage, the repulsion increases. If we increase the voltage beyond the forward biasing breakout voltage, the charge carriers have enough energy to break the potential barrier and move forward. So for a diode which is made up of silicon, 0.7 voltage is the breakout voltage, and for germanium it's 0.3 voltage. So if my supply voltage is more than 0.7 voltage, the depletion region becomes very small, and the resistance that is offered by the depletion region is negligible. So what happens is that these holes, they have enough energy, they break the barrier, they move forward, and they get attracted to the negative side of the supply voltage. Similarly, these electrons, they break the potential barrier. They break my potential barrier and they get attracted to the positive side of the supply voltage. And hence, this forms a flow of current. So we have a flow of current and a very negligible resistance by the depletion region only if the supply voltage is more than 0.7. This is the working of my P-type semiconductor and N-type semiconductor combined together in the forward biasing situation. So in the next video, we will be covering how the diode functions when connected in the reverse bias situation, the VI characteristics of the diode. Thank you for watching. Please like, share and subscribe my channel. Thank you. See you next time.